I just posted the link in the chat again to the gather.town. Hopefully you can copy it down. I'll be sure to post it again towards the end of the talk. It'll be open all day today until about half an hour after the end of the last talk, and then similarly every day throughout the conference. So yeah, you might want to copy that link, but we will keep reposting it as well. All right, so for the second talk of the day, I'm happy to introduce Tony Feng, who's from MIT and IAS, who's going to talk about Smith theory and Langlands functoriality.
Okay, thanks very much for the opportunity to speak. Can you hear me okay? Great. So here's the plan. I'm going to begin with some motivation in big picture, which comes from number theory. And then I'm going to explain some of the main results. And we're going to see that it has to do with studying a certain construction of the fork. So I'm going to summarize that and then talk about some ideas of proofs. So to begin, the motivation comes from the Langlands correspondence. And what this is it parameterizes representations of a Lie group in a liberal sense, possibly a non-Archimedean Lie group, by Galois representations into a dual group. So here G is reductive. I'll be more precise about hypotheses later. So over a global field, what this says roughly is that there should be a labeling of automorphic representations, which are algebraic, of the adelic points of the reductive group by Langlands parameters, which are homomorphisms from a Galois group into the dual group up to conjugacy. And locally, you should be able to label smooth representations of a non-Archimedean or Archimedean Lie group by Langlands parameters from a local Galois group into the dual group. And one indication of the depth of this correspondence is that operations on one side, which are kind of obvious, become very mysterious on the other side. And maybe the principal example is functoriality, Langlands functoriality. So when you have a map of dual groups, say from the dual group of H to the dual group of G, there's an obvious way to take a parameter which lands inside the dual group of H and compose it with this homomorphism to get a parameter into the dual group of G. And functoriality is about what that operation looks like on this other side, on the kind of representation theory of Lie group side. Okay, so that's sort of the general context for the questions in this talk. Now rest assured that I'm going to be sort of heading in a more representation theoretic direction. In fact, I want to start now by, maybe I can actually try to put this on two screens. I'm going to start by formulating a kind of more representation theoretic analog of this question. So anytime you have a homomorphism of dual groups from H hat to G hat, you have an obvious restriction functor on representations. And geometric Satake tells you that these categories are equivalent to categories of perverse sheaves on respective affine Grassmannians. And kind of an analog of Langlands functoriality in this context is to describe, for this functor, what does it look like geometrically on perverse sheaves on Grassmannians. And in fact, I think I hope to explain in this talk that not only are these two types of questions philosophically related because they're manifestations of Langlands duality, but also that they're kind of directly related. That if you can solve this problem, the problem of sort of geometrically describing such an operation, then that can help sort of solve this problem as well. Okay, so now let me be a little more precise about the specific results. So the global Langlands parameterization has been constructed over function fields in work of Vincent Lefort. And so we're going to be working in this situation because that's where sort of the most is known. So let me set some notation here. F will be a global function field, for example, over a finite field, for example, this one. That's the ring of rational functions in one variable. And G will be a reductive group over F. And little k will be an algebraic closure of Fp, and that will be our coefficients. And I'm going to ask that P, which is the characteristic of the coefficients, is not equal to the characteristic of this function field. So work of Laforgue and Cheng Shui have produced this parametrization of irreducible automorphic representations by Langlands parameters. So Laforgue did this under a cuspidality assumption, and Cheng Shui removed that. And now that you have this parameterization, you can ask if it has sort of expected properties. For example, if you can see Langlands functoriality. So when you have a map of dual groups, do you see some kind of operation in terms of automorphic representations? So that's very difficult in general, but certain cases of it are tractable, and I'm going to be talking about one of those today, which is the situation of base change. So this essentially has to do with sort of comparing the same reductive group but over two different fields. So just to set up the notation, let H be a reductive group over our field F. And then we're going to give ourselves a field extension, E over F, and let G be the Weil restriction of H from E to F. So in this situation, on dual groups, the dual group of G is just the dual group of H to raise to a certain power, the degree of E over F. But because we're talking about non-split groups here, even if H was split, G would not be split. We should work with L groups, which is a small, well, it's an enlargement of the dual group which incorporates the Galois action. So there's a kind of natural diagonal embedding of L groups, which extends the obvious one on dual groups. And the theorem guarantees existence of functoriality for this map. So it says that, at least under small technical assumption, that P is odd and good for G hat. And then a kind of stringent assumption that the extension is cyclic of order P. Then whenever you have an automorphic representation of H with some given Langlands parameter according to Laforgue, if you compose this Langlands parameter with this map phi, well, you get a new Langlands parameter into the L group of G, and the theorem guarantees that there is some automorphic representation which is assigned to that parameter. Okay, so some remarks about this. First of all, it's quite important that this P, which is the degree of the extension, is the same P which was the coefficient of, which was the characteristic of our coefficients. The good is a sort of small technical assumption. P bigger than 5 is always good, for example. So this rules out few cases of base change, but it does rule out a number of instances of functoriality which are not base change. So it would actually be good to improve this, and that is really coming from some kind of representation theoretic issue. I also wanted to remark that although base change seems like a rather special example of functoriality, by sort of known methods of automorphy lifting, at least under some technical assumptions, one can actually reduce sort of everything to the case of base change by basically using certain Taylor-Wiles method. There's an issue. The obstruction to doing so comes from sort of knowing whether a certain variety has a rational point, and that's a difficult question, but it always happens over some extension, some finite extension. So that was just a remark to emphasize that although this seems like a perhaps somewhat particular situation, it's actually one which is quite fundamental in number theory. Okay, are there any questions? Okay, so now I'm going
to. Maybe I can ask, what's the difference between the L group and the dual group?
Well, the L group, we can say it's like the dual group, but it has a certain Galois action, so which sort of tracks the descent datum from the split form of the group over like the separable closure to your ground field. Good question, but
that's good enough, I think.
Okay. Yeah, maybe I should also say the conclusion of this parameter, it's basically the same as saying that if you take your original Galois representation and restrict it to the subgroup, which is the Galois group of this field extension E, that comes from an automorphic representation. So if you only want to think about split groups, you can think about them in this way, that we're just saying if you restrict the domain to a subgroup, then it comes from automorphic representation, but it is advantageous to sort of to view all your groups over the same field. And for that reason, you may find yourself wanting to deal with non-split groups. Okay, so that's the global story. The local one, somewhat similar. So just to set up some notation first, I'm going to give myself a local function field, f sub v. For example, the field of Laurent series in one variable. And this notation is meant to suggest that this could arise from your global one by completing at some point. And I'm going to give myself a reductive group H over f sub v. So the analog of the local Langlands correspondence has been constructed by Geneste and Laforgue. It is what they construct as an attachment from irreducible representations of this non-Archimedean Lie group to Langlands parameters into the dual group, and they have a certain semi-simplicity requirement on their parameters, which indicates that it's not the full local Langlands correspondence. It's supposed to be, so locally you're supposed to see non-semi-simple ones as well, and that means that this thing is at best the semi-simplification of some hypothetical, more refined local Langlands correspondence. Anyway, if you were talking about things which are not parabolically induced, for example, this is pretty close. These things should almost always be semi-simple. So it's pretty good, and one can ask if it sort of satisfies the expected properties that you would expect a local Langlands correspondence to satisfy. So this talk will be concerned with the local analog of base change. To set that up, I need two groups, and I'm going to make them similarly. I started with my reductive group H. Now I'm going to give myself another field extension, cyclic of order P, and I'm going to pick a generator, a non-trivial generator, or a non-trivial element, which automatically generates, and I'm going to call it sigma, just because it's easier to write sigma than z mod p. And I'm going to let G be the Bay restriction of H from this field extension. So this is the exact local analog of the setup, which I just explained. Now, since you have this local Langlands parameterization, or at least the version that Geneste and Laforgue construct, it makes sense to talk about whether two irreducible representations of your non-Archimedean Lie groups are in base change. Namely, you ask the parameter of one to be related to the parameter of the other via this map of L groups. Okay, so we will investigate sort of what this base change functor looks like. And let me make some remarks here. Because G was restricted from this Galois extension, there's a natural way in which that Galois group acts on it as an algebraic group. And its fixed points are this group H. And so there's also a natural way in which this sigma, by which I mean the group generated by it, acts on isomorphism classes of irreducible representations of G. It takes them to their twist by sigma. And if you have a representation, an irreducible one, such that it's kind of isomorphic to its own twist, then the belief is that it comes from base change. Basically because the source of base change is something where sigma acts trivially. Okay, so such a thing will be called sigma fixed. Pi will be called sigma fixed if it's isomorphic to its twist by sigma. And if that is the case, then a short lemma shows that there is a unique way to extend the G action on pi to a G semi-direct sigma action. Okay, are there any questions about this?
This uniqueness is because we're using a cyclic group?
Not really. I mean, I don't know, you could think of it as like a consequence of Schur's lemma or something, but.
And just, you don't need a twist by a character of Z mod PZ or something?
Oh, no, you don't. I mean, it is unique on the nose. Okay, so what I'm going to do is sort of formulate a statement about the preimage of this pi under base change. To do that, I need to remind you about Tate homology. So let's observe that in Z adjoins sigma, which is by definition the group ring of this cyclic group of order P. Well, you have this element sigma, and its p power is the identity. So sigma to the p minus 1 is 0, and we can factor that in the following way. It's sigma minus 1 times this thing, which I'm going to call n for norm, because its effect on representation of sigma is to average over the group action. Now, Tate cohomology is a periodified version of group cohomology. If you had a representation of sigma, you would form its group cohomology as the homology of the following complex. You take pi, you apply sigma minus 1, you then apply n, and then you do sigma minus 1, and everything is kind of repeating in this direction. And this is a complex exactly because, as I explained in the first line, n composed with sigma minus 1 is 0. Now, this is a two-periodic complex in the positive direction. And so, I don't know, you can make it two-periodic completely by, so maybe I'll say this computes group cohomology. And if I make the full two-periodic complex, it computes Tate cohomology. And more concretely, I can just define T0 of P to be the kernel of sigma minus 1 modulo the image of this norm operator, and T1 of P to be the things in the other order. I could define the higher Tate cohomology groups, but they would all be the same as one of these. It's because the complex is sort of evidently two periodic. Now, suppose you were in the situation we had above, where you had not only an action of this sigma, but also some kind of non-Archimedean Lie group G. Then on its Tate cohomology, you would retain an action of not all of G, but its fixed points. And we've assumed that's this other group that I was calling H. Really, I should say G of FV. So Tate cohomology in this context, in the context of a sigma fixed representation, is a functor which takes in a representation of G and spits out a representation of H. And the conjecture of Truman and Venkatesh is that this identifies for you the preimage of base change. So if you have an irreducible sigma fixed representation, pi of G of FV, then any irreducible subquotient of its Tate cohomology base changes under local Langlands to not quite pi, but the Frobenius twist of pi. So pi has coefficients and characteristic p, and you can twist over the Frobenius. So let me just mention that the motivation for their conjecture comes from an analogy to parabolic induction, and in particular that Tate cohomology is the analog of the Satake functor. So when you have a principal series representation, that is a representation of G which is parabolically induced from a character, like a character of a levy, or a character of mass little torus, let's say, then there's this functor, the Satake functor, which you can apply to your parabolically induced representation and recover the character that it was induced from. And here what we're saying is Tate cohomology is a functor that you apply to a base changed representation, and you recover the thing that it's base changed from. Okay, so I do want to point, so when they first formulated this conjecture, it was a kind of post-conjectural conjecture in the sense that one would need to have first an actual local Langlands correspondence before you can ask that it satisfies this kind of property. And that's something we still don't have in full generality. However, we have something which is a pretty good approximation, which is this Genesee-Lefort correspondence. So if you believe it's conjecture, you believe that this Genesee-Lefort correspondence should also have this property. And the second theorem is that it is true, that Tate cohomology realizes local base change, or in other words, under some sort of mild technical assumption, the conjecture holds for the Genesee-Lefort correspondence. Any irreducible subquotient of the Tate cohomology base changes to the Frobenius twist of pi. Okay, are there any questions at this point? Okay, if not, I'll move on. So I want to describe some of the ideas in the proofs, focusing on maybe the representation theoretic ideas. But as you can see, these are statements about some specific construction of Laforgue or genicity of Laforgue, and so I'll need to say something about how those work. So I'm going to try to be brief here, but I am going to try to summarize sort of how this, at least how the global Langlands parameterization works, and then invoke your faith that the local one can be kind of extracted from that. So there are two, I like to think of this as having two flavors of ingredients. One is of a topological nature, and it is the one which provides kind of the source of Galois representations. Where do you find Galois, like interesting Galois actions on vector spaces? And it says you want to look at the L-adic étale homology of spaces with many symmetries, spaces with Hecke symmetries. And in the function field context, these are called the moduli spaces of Stukas, invented by Drinfeld. So this idea that you should find the interesting Galois representations inside cohomology of spaces with many symmetries actually goes back quite a few decades, certainly to early work of like Eichler and Shimura on modular curves in the number field context. So this is in some sense an old idea, although writing down the exact spaces that you want is a bit more recent. The second ingredient, which was really new to Laforgue, was of a net representation theoretic nature, and what it explains is, why does the dual group enter this story? I mean, you have Galois actions on vector spaces, but why is it that for a particular group G, they are governed by some parameter into the dual group of G? And what Laforgue explains is that this really comes from the fact that your coefficient sheaves for these cohomology groups are indexed in a natural way by the representations of the dual group via the geometric Satake equivalence. So this means that the physical sheaves are indexed by the irreducibles or let's just say the objects in this category, and then the maps between them are indexed by the morphism in this category. And from this picture, you are able to extract like many symmetries of cohomology, which eventually let you sort of refine things to a parameter into the dual group. So I'm not really going to explain that. I just want to emphasize that there are these two aspects of his construction. Okay, so let me say a little bit more about this key space which enters into this, the moduli space of Stukas. So we begin by observing that our function field, or global function field F, is the function field of the unique optisomorphism smooth projective curve, which I'll call X over a finite field. And once I have this curve, I can sort of start contemplating the paraphernalia of geometric Langlands. So there's a bunch of objects associated to it. One of them, and the moduli space of G Stukas will somehow be built out of these objects by some hybrid product. One of the objects is bun G, which is the moduli stack of G bundles on X. If this isn't super familiar to you, you can imagine here that G is GLN, and G bundles just means vector bundles of rank n. So bun G is the moduli stack of flat families of such things, and this Hecke stack is the moduli space of rational maps between two potentially different G bundles over X. So your G bundles, your G bundles might be called E. There's a map here which sends E to like E and its Frobenius twist. On the other hand, the Hecke stack parameterizes sort of rational map between two G bundles, and there's a map, the two maps to bun G, one projecting this data to E and the other to F. And so I have a diagram, I form a fibered product. That's what Stuka G is. Now this definition is not an obvious one to write down. It was something invented by Drinfeld and generalized by Warshawski and other people. And there is some a posteriori sort of number theoretic reasoning which can rationalize why this is a good definition to write down. But I don't really want to go into that. So we won't really be using in this talk at least, we won't be invoking sort of subtle properties of this space. For the representation theorists, I'd just like to offer an analogy which may help sort of ease any discomfort with how this construction looks. So I want to point out that this construction is somewhat analogous to Deligne-Lustig varieties. What are Deligne-Lustig varieties? You have a space, the flag variety of G, which parameterizes, in the case of GLN, flags on a vector space, in general, some sort of analog of that notion. And then you consider something else which parameterizes the relative position between two flags. And then you form this kind of Frobenius twisted fiber product, and you get your Deligne-Lustig variety. What we're talking about is formally somewhat similar. We instead of flags, we consider the space of G bundles on a curve. Instead of relative position of two flags, we consider a Hecke-stack, which you can be thought of as parameterizing relative positions between two G bundles on your curve. And again, you form this kind of Frobenius twisted fiber product. So as in the case of Deligne-Lustig varieties, where a feature of these spaces is that they have many symmetries, they have symmetries of a finite group of Lie type. This Stücke, it has sort of Hecke symmetries indexed by the Hecke operators of your reductive group G. And then you can look at its homology and start decomposing it and sort of refine out interesting Galois representations from there. One thing which I did want to emphasize about this is that it is the role of the geometric Satake equivalence. So it turns out that this Hecke-stack, it lives in a natural way over 1G times the curve, X, and it's a kind of Grassmannian fibration. So it's morally a flat family whose fibers are the affine Grassmannian for G. And so, well, you have a map, therefore, from equivariant sheaves on the Grassmannian to sheaves on the Hecke-stack. And you can compose that with a map from Stückes to the Hecke-stack to get sheaves on Stückes. So geometric Satake recognizes equivariant sheaves on the Grassmannian as being the representation category of the dual group. That's where the dual group enters in this whole story. And so geometric Satake provides a functor from representations of the dual group to sheaves on your space of Stückes. And that's what I mean by indexing sheaves by representations of G hat. So this allows you to index the coefficients for this cohomology by representations of G hat. Okay, let me see, 30 minutes. So yeah, so I prepared a sort of slide summarizing some features of the space of Stückes, but actually we won't really be using this, so I'm just going to skip over it. So I'm going to move on to describe sort of ingredients of the proof of functoriality. Just to recall, as I said, I'm just reproducing a slide I wrote down earlier. In order to construct this parameterization in the first place, we needed ingredients of two natures, one of a topological nature, which provided a source of Galois representations, and the other of a representation theoretic nature, which sort of explains the entrance of the dual group, explains how the dual group, how parameters of the dual group arise from the fact that these cohomology groups have coefficients indexed by representations of the dual group. And now that was a story for one group. Now suppose you want to establish functoriality between two different groups, H and G. Then you need some way to address both parts of this construction. You need something which addresses the topological part. You need a mechanism to relate the cohomology groups of Stückes for G and Stückes for H. And in the case of base change, this mechanism will be equivariant localization. So in the case of base change, there is in some natural way Z mod P action on the space Stücke G, because there was a Z mod P action on G itself. And the geometric thing we're using is that the fixed point for Stückes of G is exactly the space of Stückes for H. And equivariant localization is a thingy which relates cohomology of a space with cohomology of its fixed points. The idea that for base change, this equivariant localization should be related to functoriality can be traced back to work of Truman and Venkatesh in a slightly different setting. That being said, that's just a sort of purely topological thing. Space, its fixed points, equivariant cohomology are related. We also need to address the really specific feature of this situation, which is that you have sort of coefficients indexed by this representation category. So the second part of this two-part strategy is we need a mechanism to relate this indexing process of sheaves indexed by representations of one dual group and representations of the other dual group. And again, in the context of base change, this mechanism will come from Smith theory in a form developed by Truman and Leslie and Lonergan. Okay, so that was all the global situation. The local situation is yet another story, which I don't really have time to talk about. So let me just say that in order to extract the local Langlands parameterization, one Genesee and Laforgue sort of pull it out of the local global compatibility and in the global picture, in some sense. And for us, the issue of local functoriality will also be extracted from looking at global results and local global compatibility. So that's just to say it's another story, but fundamentally it builds on the global stuff. And I'm gonna therefore, for time purposes, restrict myself to discussing the global situation. Okay, are there any questions? All right, so I'm going to say something very briefly about topology, and then I'm going to sort of focus my attention on representation theory. So as I say that the topological input is equivariant localization. What is this? So that came from the fact that in the situation shtukas for G, where if you took fixed points for a group action, you get shtukas for H. Actually, there's something true in general. If you have a space Y and it has a Z mod P action, again, I just prefer to pick a generator to conform to the literature, then there's going to be some relationship between the cohomology of Y and its fixed points. And what you would guess is that it should say something like equivariant cohomology of Y is identified with equivariant cohomology of Y sigma. Not quite true. You need to periodify things. And what that really means is, AKA, you take Tate cohomology. So this is something we've already seen, at least for modules. I told you what the Tate cohomology was. For a module with an action of sigma, I said you form this kind of two periodic thing, and you take its cohomology. And actually, this makes sense for complexes as well. So you get a priori a double complex, but you totalize it and you take its cohomology, and that's what Tate cohomology is. And yeah, as I said before, you can kind of think of it as a periodification, two periodification of the equivariant cohomology. So once you sort of realize that this should be true, it's actually quite easy to prove it. But nevertheless, I'm not going to explain that because I want to sort of focus on the representation theoretic question which arises here. So I'll just say we have sort of sketched what the topological input is into the functoriality, into at least the base change functoriality. And now we want to zoom in on the representation theoretic input. And this comes back to the question I stated like on the second slide, which is that, this functoriality is about a map of dual groups. And how can we kind of see that? We see the dual group because we see in this story its category of representations. But the way in which we see it, actually, we see the kind of constructible incarnation of it. We see this category incarnated as the Hecke category for G. by geometric Satake. And we see the representations of the L group as the Hecke category for H. And so if we want to possibly, suppose you're given a map like this, from the L group of H to the L group of G, if you want to sort of really understand this map in the way that we're looking at things, you have to understand what this restriction functor looks like in this other incarnation as the Hecke category. Okay, so are there any questions before I move on?
Sorry, would you mind scrolling up for a screen just so I can catch something I missed? Sorry, I'm good. I'm good.
Okay. All right. So, so as I say, in the case of base change, this is where Smith theory enters, and I'm going to, maybe first I set some notation. Actually, just reproducing some notation earlier. H is at this point any reductive group over a local field. Then I give myself a cyclic P extension. There are actually only two such things, but anyway, a cyclic P extension with Galois group generated by an element sigma, and G be the Bay restriction of H. So it's kind of H over E viewed as a group over F. And again, the coefficients are an algebraic closure of FP. So I told you I'm after a certain functor of Hecke categories, which corresponds to a restriction functor on representation categories of the dual groups. There's actually a decategorified version of this question, and that was solved by Truman and Venkatesh. So they constructed something called the Brouwer homomorphism, which is a map of Hecke algebras. And under the Satake isomorphism, identifying Hecke algebras with K0 of representation categories, that homomorphism corresponds to the restriction functor. Okay, so of course, this is something which exists in characteristic 0, but the construction will sort of will use specific features of characteristic P, and certainly only makes sense in characteristic P. Now with Gus Lonergan, we have a categorification of their Brouwer homomorphism. That is a certain functor, which I call BC for base change, from the Hecke category of G to the Hecke category for H, such that under geometric Satake, it corresponds to the restriction functor on the representations of the L groups. So if you take the Grothendieck ring of this diagram, you recover this diagram. And this categorification uses some tools, relatively recent tools of modular representation theory. It uses parity sheaves introduced by Juto, Mautner, and Williamson, and it uses Smith-Truman theory in a form developed by Truman, Leslie Lonergan, and Reich Williamson. And so I hope to at least touch on why these ingredients are kind of natural. Okay, so before I tell you about the categorified version, I'm going to tell you about the Brouwer homomorphism. So what is it? Recall that we had this situation with kind of G of FV, take its fixed points, I get H of FV. Assume/believe that that this statement about fixed points remains true on certain coset spaces. That G of F mod G of O, if I take the sigma fixed points, I get H of F mod H of O. I say assume because they actually construct this in a slightly more general situation than base change, or maybe significantly more general. But and there it's not this thing is not always true. But actually, if I recall correctly, in the context of base change, it is always true. So we can just believe this is true. And what we're after is a certain map of Hecke algebras from the Hecke algebra of G to the Hecke algebra of H. By definition, Hecke algebra is equal to compactly supported functions on like 2 copies of this coset space, equivariant for the diagonal action of G of F. I'm going to describe this homomorphism in 2 steps. So first, you kind of multiplicatively average to get functions which are equivariant for the sigma action. Okay, sorry. I'm going to abbreviate from now on. This will be called G brackets, and this will be called H brackets. So the first step will be some map to function, the Heck algebra of G again, but which are kind of sigma invariant. And then the second map will be to the target we want. So this first arrow is something which just takes a function and makes something invariant by averaging over multiplication. So there's a convolution on the Heck algebra. It just convolves with F with its own translates under the group action. And that obviously produces something invariant. This first map, the fact that the fact that it's multiplicative is obvious. The fact that it's additive is non-obvious, and it's only true because we're in characteristic P. So it's similar. It's true for the similar reason that the Frobenius is additive in characteristic P. So it's something which exists for any commutative ring with a sigma action in characteristic P. The second map is a bit more interesting and specific to the Heck algebra situation, and actually it's quite easy to describe. It just takes a function, let's call it phi. This is a function on G times G, but it just restricts it to H times H. Because I want to focus on this second thing here, because that's a little more interesting. And at first, it seems like there's no way that it could be a homomorphism. Specifically, it's sort of obviously additive, but there's no way it could be multiplicative. Why? Because, well, let's just compare what happens when you multiply and then restrict versus what happens when you restrict and then multiply. So if you try to convolve in the Heck algebra of G, then you would say phi1 convolved with phi2, evaluate on x comma z. That's the same as, or that's by definition summing over sort of y's of x at phi1 x comma y times phi2 y comma z. On the other hand, if you restrict it to H and then convolve, then you really only sum over y's and H. And you, okay, yeah, morally I'm going to write restriction to H here, even though it doesn't actually affect the value. And so these two don't look like the same expression, the black and red things. They differ by, so difference is a sum over things in G, but not H, of phi1 x, y, phi2, y, z. And that doesn't look like it's zero, at least tautologically. So here's where we use specific features of characteristic P and our action. So by definition, this was G minus its fixed points under the Z mod P action. Z mod P has only two types of orbits, free orbits or fixed orbits. Once you remove the fixed orbits, you get something which only acts freely. Yeah, maybe I should write down. We're doing the proof of multiplicativity. Okay, so it acts freely, and now let's try grouping this sum into orbits. So group into orbits. And observe that we're going to observe that the sum n is constant in an orbit under the action of sigma. That's because, for example, if I took phi of x comma sigma y, by the assumption that phi was invariant under the sigma action, that's the same as phi1 of sigma inverse x y. But actually, if you think about what we're doing, we're considering functions in here. So the x is inside H, and so it's fixed under the sigma action. So this is just the same as phi1 of x comma y. So two things happen when you group into orbits. First of all, you're adding up things which are all the same over the whole orbit. Second of all, the orbit has size p because Z mod p is acting freely on it. And so actually you get 0. So it's miraculously, this map turned out to be multiplicative. And it's almost so this composition is almost the Brouwer homomorphism, actually allowed to slightly, although it is a homomorphism, it is not k-linear because of this first step, where you kind of raise it to the pth power over the coefficients. And so the actual Brouwer homomorphism is the Frobenius linearization of this thing. Okay, so what we'd like to do is replicate this story at the level of categories. we want a functor which is like kind of categorifies the Brouwer homomorphism from perverse sheaves on the Grassmannian for G to the ones for H. We can try to start it off in the same way where you average over the group multiplicatively. You can convolve with your translates under the group action. That will certainly be equivariant again. Then what happens if you try to restrict it, say restrict it to the Grassmannian for H? Well, you will be some kind of equivariant complex, but it certainly in general won't be anywhere near perverse. And if you ask yourself, like, is this thing going to be monoidal? The tricks we used in this Hecke algebra situation to see that it was monoidal will not apply at all in this categorical situation. We use the fact that when you take something in characteristic P, a function in characteristic P, and you add it to itself P times, you get 0. But if you take a sheaf with coefficients in characteristic P, you take its direct sum with itself P times, you don't get 0. So in order to make this thing well behaved, we need to kill off the stuff which we need to kill off. We need to quotient out by the things which are sort of sheaf theoretic analogs of averages over orbits, and those are the perfect complexes. Oh, sorry, I want to put this here. And what do I mean by perfect complex? So here, sigma is kind of acting trivially on this Grassmannian for H. And in general, if you have space which has a trivial sigma action, for example, it's the fixed points of something else, and you try to take equivariant sheaves on it, you just get the same thing as a derived category of sheaves with coefficients in the group ring. And that has a subcategory of perfect complexes, complexes whose stalks at every point are perfect over the group ring. And that's what I'm proposing to kill here. So in fact, maybe I keep talking in this general context. So the Tate category of Y is, or I don't know, maybe I should call it Y sigma, is the equivariant category modulo the perfect complexes. And this functor, which goes from Y and restricts it, takes an equivariant complex in Y, restricts it to the fixed points of Y, and then quotients out by the perfect complexes, is a functor. I think Jordy introduced the notion I sort of shriek star, if you think of I as being the inclusion of the fixed points. It also goes by some other names like Smith functor or PSM. And let's see. So given the time I have, I'm just going to say this functor, the Smith functor, it has remarkable properties, and it, for example, it commutes with the 6 functors. So maybe one thing I want to say is that there are a priori 2 different restrictions which one could take here, and actually they coincide. Their difference is a perfect complex, so they coincide once you pass to this quotient, and that the fact that you have something which is a hybrid of a star and a shriek restriction is really what equips this functor with its miraculous properties, commuting with also all shriek and star restriction pullbacks and push forwards. Okay, so by taking this kind of quotient, we gave ourselves a chance that the sort of formal, like monoidal properties of the functor would be good. But we've sort of strayed from where we wanted to land, which was like perverse sheaves. Now we passed the derived category and then a quotient. I do want to point out something about that perverse sheaves don't interact well with this kind of Smith stuff. So just an example, if you look at the Tate category of a point, you take the derived category of modules over the group ring modulo perfect complexes, then well, there is this following exact sequence in the derived category, but once you pass to this kind of quotient, you kill off the perfect complexes, and in particular, kill these 2 off. And so actually, in any Tate category, the identity functor is isomorphic to the shift by 2 functor. And so it's 2 periodic. And in particular, it has sort of no notion of homological degree except mod 2. That's bad news for perverse sheaves because perverse sheaves are defined by sort of inequalities in their cohomological degrees. When you take inequalities in integers and reduce them mod 2, then you get sort of gibberish. And so the perverse sheaf loses its identity when it passes this kind of quotient. Okay, so that was meant to be motivation for replacing in this story perverse sheaves by parity sheaves. They are defined like perverse sheaves. They're defined by conditions on their stalks, streak and star stalks. But whereas perverse sheaves are cut out by inequalities on their cohomological degrees, parity sheaves are cut out by parity conditions on cohomological degrees. And the right column, this makes good sense even if you reduce cohomological degree mod 2, whereas this one doesn't. So the slogan is that parity sheaves interact well with passage to this Tate category because it's reducing something mod 2, but that doesn't sort of destroy parity conditions. Just to be a little more precise, Juto, Mautner, and Williamson define parity sheaves to be complexes whose star and streak stalks have cohomology concentrated in either even degrees only or odd degrees only. And Leslie and Lonergan observed that there's a good analog of this notion in a Tate category. You have sheaves modulo perfect complexes, then you can take the Tate cohomology of their streak and star stalks, which factors over perfect complexes, and you ask that to be concentrated in either even degrees or odd degrees only. And then the point is that this Smith functor will take parity sheaves to take parity sheaves, at least under appropriate assumptions. Okay, sorry, I see I'm sort of out of time, but let me just take 1 minute to summarize how this lets you construct this base change functor. Except now we're going to sort of not talk about perverse sheaves, but talk about parity sheaves. Actually, under the goodness assumptions, these are inside the perverse. So it's not too far off. And that functor now is going to be constructed in a way pretty similar to our homomorphism. You take a sheaf, you convolve it with its own translates to make something equivariant. Then you can apply this Smith functor, and you land inside the category of Tate parity sheaves on the Grassmannian of H, of this fixed point locus. Okay, and then it turns out that one of the nice properties of Tate parity sheaves is they enjoy rigidity properties for the same reason that parity sheaves do. And this actually ends up meaning that you can lift them outside of this quotient category to actual parity sheaves on the Grassmannian. So this is essentially a theorem of Leslie and Lonergan, and they call this lifting functor LL. It's an interesting notational choice. And so ultimately you get this functor here, and this basically is that base change functor up to Frobenius linearization again. And let me just say that once one realizes that this is the construction you want to do, proving that this has the correct effect in terms of representations of the L groups is quite easy. In fact, it follows an idea of Leslie and Lonergan. You reduce to the case of tori using hyperbolic localization. In the case of tori, the Grassmannian is quite simple, and so you can compute explicitly. The reason why everything is compatible with hyperbolic localization is this fact I said earlier, that the Smith operation commutes with everything. And finally, I just wanted to remark that this functor, even though the geometry of the Grassmannian for torus is sort of trivial, at least up to the étale homotopy type of it is trivial, the functor has an interesting effect. And you can see that filtering it through this Tate parity category has the effect of like cleaning out certain perfect complexes which you want to kill. Okay, so sorry for going over. Thanks for your attention.
Are there any questions?
Sometimes in a global situation, you have a automorphic representation that is whose parameter, Langlands parameter, is fixed by sigma, but the representations, I say locally, there may be several representations locally and alternatively, I guess it's conceivable that the representation that is fixed by sigma can be the base change of several representations. But let's look at the first case. If you consider the first possibility that that sigma can permute a collection of representations locally with the same parameter.
So you're saying like there are certain non-sigma fixed. Am I understanding your question correctly? That there could be non-sigma fixed local representations which nevertheless fit into a sigma fixed L packet.
Right.
And those should also come from base change. So in other words, although I said like things like this come from base change, there are things not like this which can also come from base change. That's what you're talking about, right?
Right.
Yeah. So that's an interesting point. I think it's hard to find groups for which maybe this could happen, but sorry.
I can't think of any examples, but I'm sure there are.
Mm-hmm. Yeah, I don't know how to analyze this kind of situation. It's definitely an interesting question. But certainly, for example, this Truman and Venkatesh didn't formulate what should be true in this situation. But yeah, I don't know. I guess I'm really curious if someone knows an example of how to produce this situation. I'm sure it happens, but maybe if we start with some examples, we could start sort of try to formulate what should be the truth. Of course, if you just take like the direct sum of these and take their take homology, maybe that's like a first guess. You take some sort of direct sum of these different things that has a sigma action, and you take their take homology, and maybe that reproduces pi.
That would work for characters, for example.
Mm-hmm.
I have a question. So on the Grothendieck group, you were describing how things work in the maps between the Brouwer homomorphism between Hecke algebras.
Yeah.
And certain things, like for instance, the first half of the map, which sends f to the product of all the twists of f, how that's only a homomorphism in characteristic p. It's only additive in characteristic p. Is there an analog of this that works for, say, Ewhori Hecke algebras and at parameter q when q is root of unity?
An analog of the Brouwer homomorphism?
Yeah.
So, okay, let me say the following. So anytime, suppose you had like H is the fixed points of G, and suppose you had a level group for G. It could be the Ewhori. Suppose that it was also true that the fixed points of this were like H of Fv modulo J. Then you would have a Brouwer homomorphism. I was using lowercase. You would still have a Brouwer homomorphism from the Hecke algebra of G with respect to I to the Hecke algebra of H with respect to J. So it's not limited to the spherical case. Now, what this thing means representation theoretically, I'm not so sure, and I honestly haven't really thought about the Ewhori, like if it ever happens for the Ewhori group, although I suspect it does. Does that answer your question?
I mean, I'm more interested in the Q in the Q deformation rather than.
Oh yeah, sorry, you're talking about the Q. Everything I've said, was for like a fixed, like Q is the size of FQ. So I don't. I haven't thought about anything that has to do with deforming Q. But yeah, it's certainly an interesting question.
Are there any other questions? All right, if not, let's thank Tony again.
Mhm.
It's a very nice one. We can talk in Gather Town.